Hello everyone, and welcome to the K-Nearest Neighbors Project Solutions lecture. In this lecture, we're going to be going over the solutions for the K-Nearest Neighbors project. Let's go ahead and go to the project notebook to get started. Okay, here I am at the project notebook. I'm going to go ahead and toggle the header to get a little more room here. Let me go ahead and import the usual libraries. It's going to be pandas PD, numpy is np, and then our visualization libraries, which are going to be matplotlib.pyplot as PLT, Seaborn as SNS, and then since I'm using a Jupyter notebook, I want to go ahead and say matplotlib inline. Now let's go ahead and get the data. We want to go ahead and read the KNN project data CSV file into a data frame. So I just say df equals pd read underscore CSV, and I can begin typing out the file name, click tab, and it will autocomplete for me. I'll check the head of the data frame, which is df head, and there we have it. Again, note how this data has quite a range, so we're going to need to do some standardization once we do some exploratory data analysis. Now, since this data is essentially artificial and you don't know the actual columns, instead of doing some exploratory data analysis of these columns, we can just create a large pair plot with Seaborn, and then you can indicate the hue by the target class column. And in order to do that, it's actually just one line. You say sns.pairplot df set hue equal to the string target class, and then you can set your palette equal to cool warm if you want the color scheme to match up to mine. But you can also just use the default color scheme. Now keep in mind when you run this, since there's going to be so many columns compared to each other, it will take a while. And there it is. Now we see our pair plot. And what you can do now is maybe choose one of these squares that looks interesting to you, maybe one that has a lot of separation, and you can go ahead and explore that one in more detail. For instance, if we kind of just browse around here, it looks like there's pretty good separation based off of this column right here, which is the TRAT column. So maybe you want to do a joint plot with TRAT versus maybe MGJM or whatever. But since we don't actually know what these column names represent, we'll go ahead and just leave our exploratory data analysis there. Let's go ahead and move on to standardizing the variables. We want to import standard scalar from scikit-learn. We can say from sklearn dot, and it's under the pre-processing family. We'll say import standard scalar. And then we want to create a standard scalar object called scalar. So I'll just say scalar is equal to standard scalar, instantiate it, and then I'm going to fit the scalar to the features. So I'm going to say scalar.fit df drop target class axis is equal to 1. Because remember, I just want to pass in the features, not the entire data frame. I'm going to go ahead and run that. And then I'm going to use the transform method to transform those features to the scaled version of those features. And I'm going to go ahead and save that as scaled underscore features is equal to scalar.transform, and then pass in the same thing as we did earlier, just the features. Target class, and then say axis is equal to 1. Great. And then we can convert the scaled features to a data frame and check the head of the data frame to make sure the scaling worked. Let's go ahead and do that. I'm going to say df underscore feet is equal to pd data frame. Pass in the scaled features as my data, and then the columns, just like we did in the lecture, is going to be equal to df columns, everything but the very last column, which is the target column. And then we can go ahead and request df feet the head of that data frame. Let's go ahead and just see the first 3 rows. And there you have it. Now you can see if you can compare these values, they've all been standardized and scaled to each other, versus if you scroll back up here, these values were quite a bit larger and at very different scales from each other. Now that everything's been standardized, we can go ahead and continue on with a train test split. We'll go ahead and say from sklearn dot cross validation, we want to import train test split. And then we're going to go ahead and say train test split. And as always, my trick, go Shift-Tab, scroll down till you see the example, and go ahead and save yourself some typing by just copying and pasting this. We'll copy and paste that here. And what we want to do is set test size to 30. It's up to you what test size you want to do, and I'll set random state equal to 101, although it doesn't really matter. And we can create our x values. Remember, our x values is going to be our actual features, and that's df underscore feet. Or you can also just pass in the array itself you created, scaled features. Works either way. And now that we have that, we can go ahead and say y is equal to the target column, which was df target class. We run these two lines, and make sure you run both of them, these two cells. And that way we have our testing data and our training data. Now what we want to do is import kneighbors classifier from scikit-learn. Remember, that's going to be from sklearn neighbors import kneighbors classifier. And we're going to start off by creating a KNN model instance of n neighbors equal to 1. Which means we're going to go ahead and say KNN is equal to kneighbors classifier n underscore neighbors is equal to 1. And we're going to fit this KNN model to the training data. Meaning we're going to say KNN fit to xtrain and ytrain. And we get that out, and now it's time for some predictions and evaluations. We'll go ahead and use the predict method to predict values using our KNN model and x test. So we'll say pred is equal to KNN predict x underscore test. And we're going to go ahead and create a confusion matrix and classification report. We'll say from sklearn.metrics import classification report and confusion matrix. We can go ahead and print the confusion matrix first by passing in y-test versus the predictions, which we called pred. And since I used a different random state, I got a little bit of a different value. You can go ahead and use whatever random state. So don't worry if your results don't match exactly to my confusion matrix. That just has to do with the way you split up the data here. So if you just use the default random state, which is actually the default random state used in the solutions notebook, you may have gotten a different answer for the confusion matrix, but don't worry, that's just due to whatever number you pass in here, or if you pass in a default value. Continuing on, let's go ahead and print the classification report. I'm just using tab to help myself autocomplete some of this stuff. We'll say y-test and pred. Run that, and it looks like we're around 72% precision, recall, and accuracy. Let's go ahead and move along and see if we can use the elbow method to pick a better k value. We're going to create a for loop that trains various KNN models with different k values. Then keep track of the error rate for each of these models with a list. And you can refer to the lecture if you're confused on this step. Basically, we're going to do exactly what we did in the lecture, which is create the error rate as an empty list, and then say for I in range 1 to 40, KNN is kneighbors classifier, where the number of neighbors is equal to I. We go ahead and fit that model to our training data, both y and x, train. And then we go ahead and grab the prediction, KNN underscore predict, dot predict, excuse me, it's a method, x underscore test. And then finally, we'll say error rates dot append, and we will append the error rate, which is the average of where the predictions do not match y-test. We can go ahead and run that, and it may take some time depending on how fast your computer is. And we'll go ahead and create this plot right here to pick a better k value. We'll say plt.figure. Let's go ahead and set fig size equal to 10 by 6. plt.plot. We'll do range 1 to 40 on the x-axis. We'll do our error rates on the y-axis, and we'll go ahead and just add in some more arguments to make it look a little nicer like we have here. And those arguments are going to be things such as specifying the line color blue, line style, going to put a dashed line there, or you can just put a string with the word dashed. Set the marker equal to O, and I'm going to set the marker face color to red, and I'm going to make the marker size a little bigger, 10. And then let's go ahead and put some labels here. We'll say the title of this is the string error rate versus k. And just so we can read this, we'll say x label is k, and the y label is my error rates. Run this, make sure everything worked out okay. Great. And it looks like we get a plot that looks something like this. And it also looks like the k value, as it increases, actually kept dropping even further and further. So if we wanted to explore this a little more, what we can do is choose an even larger k value. Let's go ahead and explore that a little bit, show you what you could do if you get something like this in your real life scenario. You can go ahead and increase this to something like, let's say 60. Run that, and then change right here to 60, and run that again. And now we can see that it begins to actually flatten out after around, we can go ahead and say maybe the late 20s, so probably around 25 or even less than that, 18-ish. It looks like you're not really increasing that much accuracy for that much more k value. So let's go ahead and redo this. We'll go ahead and just choose k equals 30, since that seems to be one of the lowest points versus the actual k value. And we'll go ahead and retrain the model if k equals 30. Again, it's totally up to you what you decide what you want to do. The downside of using a higher k value is it's going to take longer to actually fit and train your model, but the upside is hopefully you get a reduced error at a certain point. And at a certain point, increasing that k value is not going to get you any more information, as we can see. Basically anything beyond 30 just kind of hovers around 0.17 error rate. So I'm going to say KNN is equal to kneighbors classifier, specify the number of neighbors to 30, fit that model to xtrain, ytrain, create my predictions off that model, predict off that xtest set, and then I'm going to go ahead and print my confusion matrix and classification report, which I can actually just grab from up here previously. So I'm going to do the same thing here, print my confusion matrix, and scrolling up again, grab the classification report. And in between them, I'm going to go ahead and just print a new line so we get a little bit of separation here. \n for new line. Let's go ahead and run this. And it looks like I was able to do significantly better with a higher k value. I was increasing my accuracy and precision recall by about 10%, 11% actually, which is pretty good for choosing a new k value. All right, I hope you enjoyed the project. Let me go ahead and do a quick run through of everything we just did before we end this lecture. We had to read in the data after we did our imports. We did a little bit of exploratory data analysis, not that much since this was basically anonymized or classified data, so you can't actually tell what the columns stand for, so it's not that interesting to explore. Then, an important step was to standardize the variables using scikit-learn's standard scalar, and then you transform into the scaled features and use that during your train test split with scikit-learn's cross-validation. And then you can use k-nearest neighbors to actually build your classifier. We start off with a low k value, fit it, check out our predictions with a confusion matrix and classification report. Then we use a for loop to choose a k value by doing the elbow method to choose a good k value. Choose a reasonable k value, retrain your model, and check the improved results. All right, hope you enjoyed the project. Feel free to post any questions to the Q&A forums. Thanks everyone, and I'll see you at the next lecture.